So in an earlier video, we have seen object detection. Object detection was presented as a capability of a neural network to present to us a stream of JSON, a JSON stream of where that contains bounding box, let's say, information about objects of interest. And in that kind of discussion, we also saw a video where bounding boxes were simply appearing in this specific frame and maybe disappearing in the next frame and reappearing in the frame after that. In many mission critical applications, it's almost impossible to deal with such a kind of a flickering appearance of the object detection output. And in fact, this appearance, this flickering that we observed in those videos originates from the fact that neural networks are reflexive in nature. So they are probabilistic devices, and as such they are reflexive in nature. So what we will do in this kind of videos, we will investigate approaches where we are going to simply try to correct these video outputs, and we will be calling this discussion probabilistic reasoning over time, where the time kind of axis needs to be involved now to correct for those and come up with a video stream that contains object detections which are very much continuous and without this kind of flickering effects. We should also mention that the topic is a bit more significant just correcting for missing frames in an object detection kind of stream. I think it can expand into covering the so-called covering the gaps, the ability of humans to cover the gaps with reason when they don't have perception information. Let's say if I'm behind an occlusion and I was visible a few moments ago, then every person who is kind of watching this scene is able to reason that, you know, this other person is behind now an occlusion. And so the kind of discussion over here will kind of expand into this type of general topic of tracking objects in a scene. So I think it's also a good idea to see the, on our side, we have this kind of block diagram that positions the topic, at least part of the topic we're discussing in general probabilistic reasoning over time. This is the yellow block over here, which follows the perception. It receives the JSON stream and delivers another stream that it is kind of richer in a sense to the planner. Richer and obviously more correct as it has stitched together the imperfect detections that we have, we are presenting to it. So out of the many areas that we can actually categorize as probabilistic reasoners over time, and the capabilities over here you see in these kind of boxes, we'll be focusing on use cases that are associated with tracking objects, as we discussed, as well also the topic of localization. And needless to say that this block is present in the what we will be calling later on Bayesian filters as in every single robot which is out there. And in fact, it is not only robots, but it's also embedded in your cell phones, as they also need to track various signals which are actually being received from the cellular and satellite infrastructure. Let's now try to establish some kind of terminology and notation on the things that we need to study to understand a little bit how we're going to go about addressing this kind of issue of correcting for imperfect, let's say, detections, or in general tracking all sorts of sensing information that is being sent to us by the sensors and also the predictors that we have in the perception subsystem. So if I may actually redraw a little bit the problem that we have seen in the kind of earlier kind of discussion, I have the environment over here, and I do have my perception block that is actually sending to me predictions about all sorts of things. Raw sensing information is coming in, and predictions are, let's say, are coming out. And then I have this system that I'm discussing about, the sort of tracking. and which we also call probabilistic reasoning over time. And then I have a planner. And finally, I have this kind of actuation or controller, if I may call it like this. And this is basically what is being fed back into this environment, so to speak, that actions are being taken are causing the change of what we'll be calling the state. So the state is what we try to predict. It is kept in the environment, and evidently the perception is actually giving us some information about what is there, let's say in terms of location of objects, let's say in the current frame, and in all frames obviously of the video stream. And the tracking is going to provide a better estimate of this kind of state to correct for all this kind of reflexive behavior that we see inside the perception system. So I think it's a good idea to take this term first, this concept of a state, and kind of categorize it. And we have plenty of states in various problems we'll be dealing with in this kind of course. So the first, I will call it level of a state, is the so-called atomic state. So in the atomic state, we simply do not care what this state consists of. Let's say you are looking at a best path to or best trajectory to exit a room, and you divide the room floor into cells, and that cell is the state that you're in right now, let's say the location, and what locations you will occupy to optimally exit the room, let's say in a shortest path or minimum cost. Then in order to solve this problem, we do not need to decompose that state of that object or robot in any finer way. So that is the sort of, so let me write it down. So planning problems sometimes use this atomic kind of states, and in general, they will be solved with search-based approaches. The second level, and planning is obviously another video, series of videos that we will sort of see a bit later. So the second level is the so-called factored states. And we've been dealing with factor states all along. So to give you an idea of a factor state that is a bit outside of the space of computer vision, let's take the description of a kinematic state of a vehicle. So I'll be calling the state S, let's say from now on. And I'll also be decorating it with subscript T to indicate that there is some kind of a time dependency on this state. And this state definitely can be decomposed into, let's say, the pose in general. The pose will be consist of, let's say, XYZ coordinates in the Cartesian kind of coordinate system. And maybe it will be associated with also three other variables, P, R, and yaw, and then maybe some velocity and some form of, let's say, acceleration. These are the so-called 6 degrees of freedom. Or DOF. In general, we have in fact, I have here also a figure in Wikipedia that kind of explains the P is the pitch, the R is the roll, and the Y is the yaw. So you have an object in general which is located, let's say here, just like my hand, and it has a pitch, it can actually has a roll, and it can also has a yaw in terms of this type of movements, to capture all these potential movements that consist that the pose of an object consists of. Okay, and then of course you have some additional ones. So that's basically a simple example of a decomposable state, and very much we are in that kind of domain all in our journey from the perception system until now. And then of course at the top of that you have the so-called structured, where actually I forgot to give an example here. Perception, localization, and pose estimation, and so on. So the example of, let's say, structure state. So in that kind of level, we are not really interested to just capture the state of an object in a detailed way, but we are also interested to create some kind of a global view of what we have right now. So for example, create some form of relationships. Capture relations between, let's say, objects. And we have, of course, neural approaches to capture relationships. These are all part of a bit more advanced discussion on visual question answering, such as relation networks and other kind of innovations in that kind of domain that allow differentiable machines to be able to capture this type of relationships. Let's introduce now the remaining kind of notation, and I should actually point out that all of the treatment over here in this kind of video and in this video series on probabilistic vision over time is going to come out of a very important book from Sebastian Thrun and his co-authors called Probabilistic Robotics. And this is, I think, a book that I think should be in your bookshelf, aside from the sort of books that we have actually recommended in this kind of course, because this will actually open the door to more advanced topics like simultaneous localization and mapping, extensions to that on, with visual SLAM, as we call it. But apart from that, let's try and introduce the what we will be calling now, from now on, the recursive state estimator. So let me write this down. Or RSE. So recursive state estimation effectively is going to happen over here in this block. And the state we're referring to is a state which is actually kept in the environment. As you know from the earlier kind of discussions, this state is stochastic, it's time varying, it is not necessarily fully observed from the agent. The agent is actually the whole thing over here. In addition to that is going to be sort of partially kind of estimated from the tracking, from the inside this kind of a tracking or recursive state estimator. So tracking and recursive state estimation is going to be one and the same thing. The state, the recursive part is because the estimation is going to actually happen recursively. So in the steps that we are now going to be discussing. Now, in terms of notation, we are going to have the first, apart from the state S of t, I need a notation about the action. So the action is actually going to happen as part of this block over here, but for our discussion, we are going to be abstracting away all of this kind of planning, let's say trajectory planning and so on, and the various kind of control subsystem over here, and we'll assume that yes, indeed, we're taking some kind of an action that will involve potentially some, let's say, some movement of the agent in the environment. So we will be denoting with A and with sub t that kind of action, and then and the convention is that the agent first takes the action. and then senses the environment. So the sensing of the environment, for that, we will have another notation. So for, I will call it the measurement. We will call it that measurement. We'll call that as ZT. We'll denote this as the ZT. And of course, the measurement, as far as this block is concerned, is whatever comes out of the perception subsystem. Okay, so we know that we have been denoting whatever prediction we are making as y hat that is actually coming out of this kind of block. Now, for this treatment, to make it a bit more compatible with the literature, we changes this y hat to the measurement ZT. But the framework also accommodates a situation where we don't have necessarily any processing over here, and we just measure with ZT whatever raw sensing information. That's the reason why I actually harmonize both options, both cases into the same sort of variable over here, ZT. Another convention we will be adopting is that we'll be adopting a convention that it is, let's say, for actions, is notational convention is we will be calling A of T1 colon T2 the sequence of actions that happen between instances T1 and T2. Okay, and the same thing will be. So let me finish this kind of a measurement. Measurement ZT may accommodate. Actually, not accommodate, but represent predictions. Predictions from the perception subsystem. Or raw measurements, raw sensory information. Also, generally, we will be discussing sequence of measurements from from between T1 and T2 with this colon kind of notation. This colon notation originates also from a language called MATLAB, from MathWorks, and for those who are working in the robotics space, in control theory and things like that, are very familiar with that kind of tool, as it is kind of monopolizing some of the domains over there. Okay, so now that we have introduced, if you like, these variables, we would definitely going to be expressing probability distributions, and we'll be dealing with probability distributions all along in this discussion. And we need to define some assumptions regarding this structure of these probability distributions. But in general, we will be discussing a probability distribution that involves the state, the probability of being at a state S at time t, that is called ST, given the sequence of previous states, let's say from the beginning of time until t minus 1, comma, the sequence of actions from 1 to t, and the sequence of measurements from 1 to t minus 1. Okay, so this is this is going to be the third important kind of concept that we need to introduce here, and we will be calling this generative model of state evolution. We will be calling this state transition model. Is a generative. Generative we call all, of course, approaches where we are actually going to be creating this probability distribution. So it's a general, and of course this reminds us the discussion we had also in classification in terms of generative versus discriminative kind of classifiers back when we're discussing this in that kind of video. So state transition model is a generative model for the state evolution. So the the important kind of piece to recognize here is the following. I'm taking some measurements. I am evidently processing them in the perception system, making some kind of predictions where I'm correcting and tracking whatever is coming out of the perception subsystem. I am creating, if you like, plans based on that information. And then these plans are executed by the controller who is taking actions. It is going through these actions are changing the state of the environment, let's say an action to move. And that change state is being observed again by via the raw sensing measurements from the perception system. And the whole thing is kind of constantly evolving. And this evolution of state is what we are going to be capturing by the so-called state transition model. How probabilistically the state will actually change given previous states. And as we will see a bit later, in fact right now, we'll make an important assumption regarding the completeness of that state. We'll make this what is called a Markovian assumption. And now we will discuss that kind of assumption in detail. So a state ST is going to be called complete if it is a complete, that's why the name complete is a complete summary of the past. In other words, S of t is a sufficient statistic for all past measurements and actions. So based on that, this is also known as the Markovian assumption. And this actually, it is that assumption that actually simplifies quite a bit a lot of the probability, this conditional probability distribution we just wrote, which I'm going to repeat now. So we wrote this S of t, probability distribution of S of t, given the previous states, the actions up to this moment in time, t, and all previous kind of measurements. And this is what allows us to write it as follows. This assumption, P of S of t given st minus 1, comma, A of t. And this is a much simpler probability distribution that we will definitely going to have some hope that we will be able to estimate. And given that sort of assumption that we actually made over here, I think it's worthwhile kind of going a little bit over it. So we say that obviously the measurements that are are not really needed at all, because at the end of the day, the only thing that matters is really the previous state, S of t minus 1, because the state is complete. And but the current actions, so previous actions are not needed, but definitely out of all actions, the current action is needed, because it is really the current action that induced the state transition. So let me write it down. Action at t induces the state transition from st minus 1 to st. Okay, so that's why we have to have, and considering that kind of action, in other words, then we have this transition. Okay, the specific action A of t. And now we will need to introduce another, the second probabilistic model. So we are going to have two main probabilistic models what we have to introduce. So we introduce the state transition, what causes the states, of course, the current action, and the simplifying assumption that allows us to capture that. And the third and the sort of second probabilistic model is going to be called the generative model of the measurements. So we have to have a probability distribution, that a model, in other words, that will capture those measurements. So again, we will making this assumption, given the complete state of the assumption, we'll make the following, can actually write the following equation. So zt is now the random variable, and we have this measurement that we are getting at time t will depend on previous sequence of states and actions that we have taken, and also previous measurements from 1 to t minus 1. And this one, based on that kind of assumption, can be written as P of zt given st. And it's actually also important to just spend a couple of minutes trying to discuss that kind of simplification. The fact that let's say I'm moving from, I have moved and I actually have reached this kind of state, let's say next to this kind of desk, that state that I'm right now is the only thing that I need to consider and therefore condition on in order for me to specify the probability distribution of, let's say, how far away that let's say a sensor will bring me on, how far away I am from this kind of obstacle of that wall, or let's say the desk over here. So that is what this probability distribution is actually capturing. For example, we'll be assuming, and a bit later we'll be assuming that this probability distribution has could be continuous, and it will be let's say or discrete, and will take some kind of distribution around it. Let's say for continuous will be a Gaussian. Okay, and so that is the second kind of model. So we have now two models. One governs the state transition, the other governs the measurements. And we also need to have some representation. It's not a compulsory thing to have a representation of the problem statement in a graphical kind of form, but this has been really the norm in this kind of domain, to represent random variables as nodes, and with as edges, with arrows, the transition, the evolution of those probability distributions. In fact, these arrows in this case will indicate dependencies. Okay, so we will be calling this representation the dynamic Bayesian network. It's dynamic because it's going to be time varying, and Bayesian because we will be creating, if you like, a filter, as we will call it, call a Bayesian kind of filter, that it will be able to give us good estimates of what we'll be calling now a hidden state. So let me write it first. So in this kind of Bayesian network, which is also known in this case as a hidden Markov model, or HMM, we will represent it as the states are represented with this kind of circles. I'm going to write just three states, st minus 1. This is obviously my hidden state. I do not know that kind of state. It is that state that it is in that kind of environment kind of box. And that state is dependent from the action, because the action will induce this transition from st minus 1 to st. Okay, and then we have evidently we know the action. We will assume that we know the action that the robot or the agent has actually taken. And in the literature, we are shading this. Whenever you see a shaded kind of node, then this kind of node is not a random variable, but it is a known value. It takes a known value. In fact, I don't need these dots because I'm only going to draw just 3 states from st-1 to st+1. st+1. And this is going to be my at+1 action. And the other node is the measurements, the measurement node. Obviously, I'm going to be assuming here that I'm going to be getting some estimate out of the measurement. So some kind of a raw value from a sensor, or from as a predicted value from, let's say an object detector. ZT, and we have ZT+1. Okay, so, and this continues into the future. So the arrows, of course, are the dependency. The measurement I'm getting evidently is dependent on the state I am, and the action and the current state is inducing that kind of state transition. Okay, so we will be need now to define what we'll be calling some 2 key posterior probabilities that represent the state. And this will be called the beliefs, 2 different versions of the beliefs that we have about whereabout we are in terms of state. Okay, so note that the state is the hidden node, the hidden variable. And that's why the model is called hidden Markov, because we don't have any dependency from this state other than the previous state and the current action. And that is what was expressed over here. And model, because evidently we are dealing with these 2 probabilistic models that actually define this diagram. And this is also known in the past as probabilistic graphical models, and people have been devising for a couple of decades now specific algorithms to be able to provide inferences, do inferences given this kind of probabilistic dependencies between random variables. Okay, so the first posterior, which I'll be calling the belief hat of ST, and I'll symbolize it with belief of the state ST, but this hat will mean something, is the probability of S of t given at, so from 1 to t, and previous measurements. Now we will simplify this posterior also, but this belief hat will be the belief, will indicate the belief of being in state S of t before, that's the emphasis, before taking measurements ZT, before receiving measurement ZT. And that's why the index ends at t-1. Okay, so this is the belief, and we'll see now the belief hat, and this is we'll see in a moment how the 2 are involved together, how we are going to use them. So the second posterior probability distribution that I want to specify is the belief of being in state ST, and this is the posterior P of ST given a from 1 to t and c from 1 to t this time. So it's exactly the same thing, the belief after a receiving measurement zt. And after receiving measurement zt. So these are the two, I will call it key posteriors that we will need to start finding a way, a recursive way of estimating. Evidently, we need this. And then what was going to happen in this kind of recursion is that if we have, given, if you like, the diagram, if we have an estimate of the belief of this kind of state, an estimate, a posterior probability of being in that kind of state, then we'll be updating that in the next time. This will actually be used next time to come with an estimate of this posterior at t+1. Now we'll need to see how this is going to be done.